Okay, so this week we have another 5 problems, and they're kind of, I guess I picked for the most part, the theme questions are more related to the knapsack problem that we discussed a little bit last time. And I want to reinforce this by giving you 3 different knapsack problems. One of them actually turned out to be a little bit more involved, but we'll go through them anyway. And even if you don't um, do it or completely understand it, it will still be a good illustration of a new technique that you have not seen before, perhaps. All right, so as usual, we have 2 easier problems. So I'm actually going to start with problem B. Uh, there's not too much to say. So if you read the problem, basically you have 2 numbers, left and right. If they are the same, then you say it's even, and then the number of points that you're supposed to produce, it's just the sum of the two. If they're different, then it's an odd moose, and it is twice the highest number of times. So basically, take the 2 numbers, take the maximum, and multiply by 2. Um, so you have a bunch of inputs. There's actually just one input, L and R. If L and R are different, you say odd and then multiply uh, by the maximum of the 2 numbers. If they're even, so if they're the same, then it's just even, and then you just add the 2 numbers. If the moose has no tines, I'll put not a moose. Okay, so this one, there's not really much to say. So I'll just go straight to the code. You read in the left and right. Um, if the two, so this is just one way to check if they're both 0, but of course, other ways you can check they're both 0, doesn't really matter. So if they're both 0, then it's not a moose. If they're both the same, then it's an even followed by the number that's just the sum of the two. And then if it's otherwise, it's an odd, and then I multiply by 2 times the maximum. And that's pretty much it. Okay, so as I said, there's not a lot interesting to say. So we'll just move on to the next one. Okay, the next one, it's a little bit, how should I put it? It's a problem that if you don't know anything, or if you don't know too much, you might just do it and then you get it right away. If you know a lot, you do it right away and you get it right away. But if you kind of know a little bit, but not enough, you might just get stuck. So let me explain what's going on. So you have a bunch of problems. So Thomas created some problems so I actually work on. Each problem has 2 integers as a lower bound and an upper bound skill level. So each programmer has an integer skill level. If someone with a skill level between the lower and upper bounds of the problem inclusive, and they solve that problem, then their level go up by 1. Okay, so if you want to solve a problem, your current skill level has to be between the upper and lower bound. And if you can solve that, and if you choose to solve it, then your skill level will go up by 1 from that point on. So Ashley trained on Tom's curated list of problems as follows. She'll look at the first problem on the list and either decide to solve it or skip it. Then she'll repeat this for every problem on the list in the order that Tom loaded the problems. Once she has skipped the problem, she can never go back. Compute the maximum skill level Ashley can have if she chooses to solve and skip the problems optimally. Okay, so there's this problem of optimally, right? So when you get into a problem, so you have to look at problem 1, problem 2 in that order. If you see a problem that you cannot solve because your skill level is outside of the range, then, well, there's nothing you can do. You just skip it. But if there's a problem that you can solve, then there's a question of do you solve it and increase your skill level by 1, or do you skip it in the hope that maybe you will solve more problems later. Okay, so that's basically the issue. So for each problem that you can actually solve, right, you can decide to solve it or skip it. There's 2 choices. And by solving or skipping it, it changes your current skill level So that can affect what you can solve later on, right? And your goal is to maximize the skill level. Now, the only way you can increase skill level is by solving problems. So maximizing a skill level is actually the same as maximizing the number of problems you solve. Okay? So first line contains two integers, n and s. N is the number of problems. S is the current skill level. Each of the next n lines contains two integers, L and R, that are between 0 and 2 billion. And these are the lower and upper bounds for the skill levels of that problem. And I'll put a single integer, which is the maximum skill level that Ashley can attain. Okay, so everything fits inside roughly 2 billion. So a normal 32-bit integer will work. So that's not an issue. But there are a lot of problems. There are 100,000 problems. So when you see one that you can do, you cannot afford to try both ways. Like there would be 2 to the n. If you potentially, if every problems you can do, then you can do 2 to the n, 2 to the n choices, which is way too much. And then you might say, well, what if I choose one way, recurse? What if I choose the other way, recurse? Well, what happens later on depends on your skill level, because when you solve a problem, your skill level goes up and that changes what you can solve later. So your recursion might need to remember your current skill level and also how many problems you have left. And that, again, because the numbers are so big, that's also not really feasible. So the question then is, if I have a bunch of problem, right? P1, let's go P2, P3, P4, up to Pn. Okay. I have to choose a bunch of problems to solve. I want to choose as many as I can to maximize my overall skill level at the end. So I look at the very first one. Okay, if my current skill level S, it does not fall inside the skill level required for P1, then I can just throw that away. There's nothing I can do anyway. Okay, so I might as well assume that the first problem I can actually do, right? Because I can just throw away anything that I can't do and ignore it. So the question is, if I can do this, should I do it or should I not do it? Okay, so imagine that I have some optimal solution that I mean, I don't know what the optimal solution is, but suppose we know that some optimal solution exists, maybe it's not unique. And suppose that in this optimal solution, we decide not to do P1, but do something else later. Maybe we do P3. That's our first problem that we choose. So for some reason, we decide to choose the optimal solution, decided not to do the first problem, but decide to do problems 3 first. And then the rest of it. It will do a bunch of other problems. Okay. And whatever that number problem is, let's say it does M problems. So the optimal answer is M for number of problems it can do. And it decides that it does P3 first. Now, what does that mean? That means that if you skip the first 2, the skill level is still at S at this point. So P3 must be a problem that's doable by its current skill level S. And then from this point on, whatever you do, you start with skill level P plus S plus 1 because you just did a problem. Now, imagine that I just do P1 because S also falls in that. And from this point on, I am at S plus 1 because I did a problem, my skill level is S plus 1. If I decided just to skip these two, right, just to skip P2 and P3, and follow whatever problems I choose to solve in here, I would have obtained the optimal answer too. Right? So if there was an optimal answer that doesn't require P1 to be solved, I could have actually not solved this problem and solved P1 instead, copy the rest of the solution, copy the rest of the problems that I solved, because if you can solve this one can be solved by s plus 1, this one can be solved by s plus 1, because I'm at s plus 1 now. This one can be solved by s plus 2, so this one can be solved by s plus 2. I could just copy this optimal solution with the only change being that I choose to do the first problem that I can do. And I would not have made the solution any worse. So what does that mean? That means that if I have an optimal solution that doesn't choose the first problem that you can do, you could arrive at another optimal solution by choosing the first problem that you can do. And now we can kind of get rid of this problem. And then recursively make the same argument and say, well, if this problem, now that we have done this one, now we can say we start at skill level s plus 1. And if there's this optimal solution where P2 can be done, but P2 is skipped, then you could have chosen P2 and still have optimal solution. And can recursively do this and basically argue that no matter what happens, whenever there's a problem that you can do, just do it. And that is always no worse than the optimal solution. In fact, that means it's an optimal solution. So it may be that there might be other ways to get the optimal solution, but taking the first problem that you can do and do it will always lead to some optimal solution. And this, if you have taken 3620, it's what is called greedy algorithm. Right? Greedy algorithm says you go through your choices in some order. So in this case, it's just the list of problem in the order that you're given. And for each choice, you decide to make the choice and you never look back. Once you move on this, you never go back. So this is, in fact, the problem statement actually tells you that once you make a choice, you can't go back. So this is basically a greedy algorithm, the basic setup of greedy algorithm. And in some problems, the greedy algorithm is actually optimal. Not everything. For many problems, the greedy algorithm is actually very far from optimal. But in this case, you can prove that doing the greedy algorithm will actually work. Greedy algorithm is usually really easy to code, but much harder to prove that it's correct. So in this case, the general way of proving that a greedy algorithm is correct is to say, let's get to a point where you have a choice to make at the very first choice, and let's pretend that there's an optimal solution that makes the other choice, right? So here, the optimal solution decide not to choose P1. Then you show that you can take that solution that doesn't choose the first problem you can do, massage it to make it choose the first problem they can do. So choose the first one, but get rid of this one, and still maintain the optimality of the problem, of the solution. If you can do that, then you can show that the greedy algorithm is no worse, and therefore the greedy algorithm is good enough for the optimal solution. And this kind of proof is often called exchange argument or exchange proof, because I am taking an optimal solution that theoretically exists that did not make this choice, the greedy choice, and we exchange that choice with the greedy choice and still maintain optimality. Okay, so I started off saying that this problem, if you don't know too much, you might just decide to do greedy and then not worried, not even realize that there might be a proof that's needed, and you do it, and then it's easy. If you know a lot, you can prove this, and then you say it's easy. But if you can't know a little bit more, and you say, well, maybe the greedy is not the right thing, but you don't know enough to prove how to prove that it's the right thing, then that's where you get stuck. So at the end of the day, after all of this, What is the conclusion? The conclusion is all you have to do is go through the problems one at a time and keep track of which problems you can do. And as soon as you see one that you can do it. So here's the solution. I wrote a lot of comments, but I mean, the code itself is relatively easy. I read in N, I read in S, go through each problem, read in L and R. If it's in the right range, I do it. And when I do one, whenever I do a problem, then the skill level goes up. Okay? And then you just keep track of it. So, yeah, basically, this problem, it's really easy to code, but a little bit harder to prove that the solution is correct, I guess. Okay, weights of words. So now we're going into the dynamic programming knapsack type of problems. Now knapsack, let me just kind of remind you what a knapsack is. So knapsack usually has something of this setup. Okay, so you have a knapsack of a certain capacity, capital C. And then you have a bunch of items of weight, WI, and cost. Okay, maybe I shouldn't use. Okay, let me use capital W for the total capacity. Some cost, CI, or some value, let's say. It doesn't matter whether it's value or cost. Okay, so value. The original knapsack problem is about value, I guess. Then you want to choose items so that some of the chosen weights, it's at most the capacity, so you cannot choose more than what you can carry in this knapsack. And you want to maximize total VI chosen. So if you have a backpack or a knapsack, you have a bunch of things you want to bring, you can only bring what you can carry. But out of all the things that you can carry, you want to maximize the values of the things that you took. Now, there are many different variations of this problem. This is sort of the basic knapsack. It's sometimes called 0-1 knapsack. Why? Because each item is only used 0 one time. Either you choose it or you don't. There are other kind of knapsack where each item can be used 0 or more times. So maybe you have a different types of things you can take, and for each type, there's a value and weight, but each type you can pick more than one of those if you want. So that's really the same idea, but the coding is slightly different, but it's really the same idea. You could decide to minimize the value. So instead of these item having certain values, maybe they have a certain cost, and you want to minimize the cost. Doesn't really matter whether you maximize and minimize. It's the same problem. You can also count the number of ways to do something. So instead of maximizing total value, maybe there's no value, and you just want to know how many different ways can you form this, can you pick items to have a capacity to satisfy the capacity limit. And there are many, perhaps, other variations. Okay, so it doesn't really matter which variation we look at. The idea of how to solve it is essentially the same. So the first thing to realize is that these problems, if the problem's large, this is basically hopeless. It's what we call NP hard. For those of you that don't know, NP hard basically means, in a very, very rough sense, they are very hard problems that nobody knows how to do. And the only ways that we know how to do it, it's not polynomial time, although this NP does not mean not polynomial, it means something else. But there are no known polynomial time algorithms for solving these problems, and therefore it's basically hopeless. Okay, so you're probably never going to be asked to do this type of problems if the problem is large. But what is large? Okay, large means something very specific. And we'll talk about, I guess, easier way to say is what is not large. And usually we can solve it in, so let's say n items, n times w time. So that looks pretty small, n times w. And you may say, well, why is that not polynomial? It's just n times something, and that's just two input parameters. But the reason is that, for example, if w is, I don't know, 1024, which is not that big. So if you have 1,000 items and 1,024, that's n times w is only 1,000,000. So you say, wow, that's not too bad. But actually, the way that we normally talk about complexity is we want to talk about complexity in terms of the input size. So what is the input size here? Input size here is n items, right? So n items, so n times something. You need a certain number of bits to store the weight. You need a certain number of bits to store the value. But this w can be stored in this many bits. Actually, it's like this. And it's this part, big O of n, like this. And then w is only this part. So w, even though the complexity is w, in relation to the input size, which is log of that, this is actually exponential in input size. And that's why this algorithm, this solution that I'm going to talk about, it's not a polynomial time algorithm. People call it a pseudo polynomial time algorithm. Okay, but it's actually exponential time. But anyway, for most programming context problems, especially the ones that they expect you to solve by dynamic programming, you would look at n, you look at w, you multiply, and if it's not too big, then you have some hope. Otherwise, you have no hope. You need to have some other way. Okay, so how do we solve this problem? The idea is that you ask, instead of just you have n items, total capacity W. Now, just because the capacity exact is W doesn't mean you have to use exactly that amount. You can use any amount less than that because you might not be able to fill it exactly. But anyway, we're going to solve for this F, and let's call it, sure, I'll just let me use different variables. K T, let's call it. We're going to say, for now, true or false. True if it is possible. So we're doing the 0-1 knapsack. If you do more than, if you have one multiple copies, then we have to adjust this, but we'll just do the 0-1 knapsack. If it's possible to form, so to choose from first k items with exactly total weight t and false otherwise. Okay, so we're not just doing true or false for now. We're not even maximizing or minimizing the values taken. We just want to know, can we even form the sum? Okay. Well, so that, and what we're going to do, if we can if we can choose a bunch of things to make up capacity, would just be try f of k0, f of k1, f of k2, where f of k0, it's always possible because you can just decide not to choose anything. Okay, so you can try all of these, and if one of them works, then you know you can do it. Now, if you don't want to count the case where you don't choose anything, you just don't try this one. If any one of these works, you know that you can pick something. Okay? That makes the capacity up to M, but to W. Okay, so how do we do this? Well, the idea is that if you want to form a capacity T using the first K elements, K items, you can decide either to use the kth item or not. If you decide not to use the kth item, then you just kind of remove it. You still have to form the same sum. And you just kind of ignore this, the last element. So you just recurse with one fewer element item. Or if you use it, you still remove the item, but then the sum that you have to form is T of T minus Wi. And it's going to be a Boolean OR of these two things. So either you can do it with the kth item or you don't. So K minus, sorry, this should be K minus 1. And then base cases, if you have 0, if you have no item and you want to form the sum 0, that's true. If you have no item but you want to form any other sum, that's false. If t is greater than 0, and also, I guess if you want to form the sum 0 of any items, it's also true because you can always just don't select anything. So these are the base cases, and this is to decide if you can actually form the sum. And you can write this in a recursive way with memorization. And this table that you're going to use would have n items in this entry. Okay, or n plus 1, depending on how you, because you go from 0 to n. And this will have w plus 1 entry. So altogether is n plus 1 times w plus 1, which is basically n times w. Okay, now, this is the Boolean case, but actually I want to minimize the values. So what I'm going to do is I'm going to change this. Okay, I'm going to change this up a little bit. I think I'm trying to maximize. So the maximum possible value, total value of the items chosen, or if it's impossible, maybe we'll just make it 0. Okay, so it's not possible. And then if you're trying to maximize the possible values, then you would be maximizing of these things. Okay, and let's look at the base cases. If you have 0, if the sum is 0, then you just don't choose anything. Oh, by the way, I'm assuming, of course, that the weights and the values of everything is non-negative, right? If it's negative, then things becomes a little bit tricky because you can take something to somehow erase capacity. And then here, this is also 0 is impossible, right? So all the base cases are 0. All right. So how do we do this? Again, we're basically doing, it's two choices. Either we do it, or either we use the kth item or we don't. If we don't, then we basically just throw away that kth item and we ask again recursively, solve for k minus 1 items with the same total and the best cost, it's whatever it gives me recursively. If I were to use the kth item, I recursively try to use the k minus 1 items forming this sum. But now I also include the cost, the value of that item, because I just picked that item. And I want to, in this case, maximize over these two things. Oh, by the way, this, if WKI k minus 1 is bigger than t, then this can be negative. And you have to decide what to do with negative. Either you don't include this sum because you basically can't put that item into the knapsack, or you change them to the base cases to say that if t is ever negative, just return 0, impossible, or something like that. Okay, so I forgot about this before, so you have to worry about this case. And that's basically it, right? And this will give you the maximum value. Now, what if you actually want to know not only the maximum possible value, but actually tell me which item did you use to form this sum? Well, what you do is you can have an auxiliary array. I don't know what you want to call it. A Boolean solution array that has the same dimension, and whenever you compute this, it's either going to be true or false. So if it's true, if using the kth item gives you the bigger number, and false otherwise. And then you can use this array to figure out, okay, I want, maybe, so this should not be, this should be n. So you know that the best result is f of n, I don't know, 35. Okay, so you know that's the best result. So you go and look up the solution table for n and 35. It'll tell you, yes, use the kth item. So that means that I need to use the last item. So that's part of my solution. And knowing that I use this, then I can recurse this way, and I can look up solution of k minus 1 and t minus wn minus 1. And then based on that, I know whether I choose the second last element, and so on. And this is what is called tracing back the solution. And it's a common way of getting this if you're interested in more than just the solution, just the optimal value, but actually which way you selected this. Okay, now there's another version of the problem. I said count the number of ways you do something. So count the number of ways you can form. Actually, maybe it's easier just for me to erase everything and start writing. So maybe I want to say f of nw and t is the number of ways to form the capacity, the total capacity or total weight T using first, I guess I was using K items. Okay, so it's the same idea. F of K T is either F of K minus 1, oops, T minus weights I, K minus 1. This is either I use it or I don't. And this time, instead of picking the max or the min or whatever, or I just count them. I just add them. Again, this, if T minus K minus 1 is negative, don't use this term. Just get rid of it. And then you have the base cases, F0, 0, F K0, and F 0T. So F00, how many ways can you make the sum 0 using nothing? And this is something that's very commonly messed up if you're not used to this. The number of ways to do nothing, it's 1, because you can choose the empty set. Okay? And here, this is the same. The number of ways to get 0, it's also, again, I'm assuming that the item always have a non-negative weight. Sorry, a positive weight. So if you have an item that has 0 weight, I guess you can always include that. But assuming that you don't have any items that have 0 weight, then the only way to make 0 is by not doing anything. And then if t is greater than 0, then the answer is 0. There's no way you can do it. So these are the base cases. And that will count the number of ways you can form a particular sum for a particular capacity T, a total weight. Okay, so having said all of that, what is this weight of words business? So I want to make 40, up a string of a certain length L up to 40, and I want to sum up the weights. Each character that I choose has weight 1 to 26, depending on which letter you have. And you want to choose a bunch of letters. You want to choose exactly L letters so that it sums up to exactly the W that they give you, if possible. And if it's possible, print any string that makes sense, that satisfy this, otherwise say impossible. Okay? So here, basically, we have 26 types. Okay, you can say that the knapsack has capacity 40, I guess. So, okay, let's backtrack. What is the capacity of the knapsack and what is the value of the items? What are the items? Okay, so our knapsack here, we're trying to sum up to something. So in this case, our capacity, it's actually the total weight W. That's my capacity. And in this case, I actually want to hit the capacity exactly. The items are the letters. And they have weights, Wi, 1 to 26. I want to pick exactly N of them, or L of them, so that this will sum up to that. So my question is F of L, well, I guess I used the same letters from before. Hey, T equals, is it possible to form total weights T using K letters? And if not, I do something else. Okay, so if it's not, I'm going to use 0. Now, if it's possible, I can say 1, but I'm actually going to say the value of letter to start this string. Okay, so value is either 1 to 26. So what am I going to do? Right, so I'm using the same idea. So for each position, so K position, I'm going to look at the first position. Now, this time, it's not that I can decide to choose an item or not choose an item, but rather I have to choose one of these 26 items. So I'm just going to try all of them. So f of k minus 1, t minus 1. That would be A. F of k minus 1, t minus 2. Because the item has B has weight 2. Dot, dot, dot. So I tried 26 different things. And if any one of them comes back as the non-zero value, then I pick that one, then that's okay. That means I can do it. For example, if this one comes back as non-zero, it means that if I choose the first letter as B, I can continue and finish. If none of them gives me, if all of them gives me 0, then that means I cannot do it no matter what. Okay, so I know that I went by pretty fast, but given that I spent quite a bit of time talking about knapsack in general, hopefully this is more easy to understand. So I have this, what I call memorization table. Basically, all the different ways I can call this function f, length and weight, total weight. Total weight is at most 1,000, so I have to go to 0 to 1,000. That's 1,001. Length is at most 40, so it's 41. And 0 if it's not possible to form the string of length L. 1 to 26 if you can do it by starting the string with these letters, and -1 if it's uninitialized. So at the beginning, before I start anything, I initialize everything to be -1. So I fill the whole table to be -1. So if you call this function, because I don't want to type mambo LW all the time, I do a reference like this. So whenever I use the answer, it's referring to the same set, and I can assign to it. Okay, so if the answer is at least 0, so if it's not -1, that means I've already computed. So I just return it. I don't do it again. Now, base case, if the length is exactly 1, if there's only one letter, then it's relatively easy because either the total weight that you're looking for is between 1 and 26, in which case you just pick that letter, or if it's outside the range, well, then you say you can't do it. Okay, it's 0. Otherwise, I try all 26 choices, and if the recursive approach, using one fewer letter and getting rid of that weight from the total, returns something non-zero, then I know I can choose the letter I to continue. Now, one thing though is that because it's W minus I, I'm doing that. So I will only do that if W minus I is not negative. So if my weight is like, I don't know, 15, I'm not going to try 20 because this will be negative. Okay, so here I skip things if the letter I try is too big. And of course, if I try everything and I haven't returned because I haven't found anything that works, I also say it's not going to work. And so that's basically it. I call f of LW my original input size. And if it comes back at 0, I just say impossible. Otherwise, I go through, I don't know why I go through this in reverse order. It doesn't really matter whether you go forward or backward because the sum of the letter weights are the same. So for some reason, I decide to go backwards. But anyway, I looked at the table, the value of the table, and okay, I go backwards because that's how my recursion works for L and W, because I always go back 1 0 at a time. So that's why. Okay, so I go backwards, I read off the table entry for L and W originally, that would be the first letter. That would be a letter I use. But remember, it's 1 to 26, so I have to subtract 1 to go from 0 to 25, and then add the little a to get the ASCII value of the letter I want, and then convert it back to character. And now that I printed the character, I need to adjust the weight that I'm looking for. I have to get rid of the weight of the character I just printed, so that when I go down to the next level with 1 field length, I would use the correct W to look up the next character to use. Okay, so the tracing back, you need to sort of maybe get a little bit used to, but basically this, whatever you do in the recursion when you compute the dynamic programming table, right, L minus 1, so I'm looping down by 1. And here I'm W minus I, but what was I? I was the answer. So I W minus the answer, so that this W is going to be looking up the same thing. So you have to trace that the same way that you do the recursion in the computation of this table. Okay, the next one, it's a, I don't know, very simple knapsack. As simple as in the standard knapsack. Each case have a capacity of 2,000, an integer of up to 2,000 items. Each item has weight, and each item has value and weight, which are between 1 and 10,000. Now, anything that has weight bigger than 2,000, you can pretty much ignore because you only care about 2,000 capacity anyway. But anyway, you want to choose items that have maximized greatest value. Okay, you want to maximize the values chosen. But in this case, you also have to produce which item you chose. First item has index 0, second, but anyway, that is exactly what I talked about. So I'll just go straight to it. So I have this best value, and then I have a Boolean that says true or false. So this is what I described. And okay, so this is just basically solving many cases. This reads in the input, reads in the value and the weights, fill in the table with -1 to initialize it, and then call f of cm. I guess in this case, when I wrote it, the capacity is the first parameter, second parameter is the number of items, but it doesn't really matter which way you do this. So first, as usual, check if I've already computed it. If it's 0 or more than the computed, then do it. Just return it. Base case, if case equals to 0, no more object, then basically the best value is 0. There's nothing you can do. Yeah, don't pick anything. Otherwise, either you decide not to choose one, so you recurse on smaller number of items but same capacity, or you try using it if the item fits. So the recursive value is the recursive value plus the chosen item. And if this is better than the value so already computed by not using it, then I set the best value to this one, and also remember that chosen is true. So I compute that, and then I call this trace solution. So solution, just remember the vector of items stored, and trace is the function that does the magic. So if it will follow the same as the recursion, so of the computation of it. So if k is equal to 0, well, if k is equal to 0, you don't do anything. So if k is equal to 0, you don't do anything. Otherwise, you look at chosen ck, either you chose it or you don't. If you choose it, then of course you remember that you have chosen that, but also you recurse in exactly the same parameters. Okay, c minus w, k minus 1, and k minus 1. The v is just the vector to collect the indices that are chosen. Otherwise, if you didn't choose, you recurse exactly the same way as when you computed and you didn't choose it. And then I guess you print it out. Okay, so this is a very standard knapsack thing. And it would be really, really helpful to implement this. Even if you're just following exactly this code, just so that you do it at least once in your life, right? This is something that is very, very standard. There are many things that you can do with this kind of problem. Okay, the last one, I picked this problem because some lists of there's some list of caddis problems done by categories and so on. It says this is an abstract problem, and I chose it, and I thought, oh, it's an abstract problem. I did it, and then it came back, takes too long, and then I looked at it, and then I didn't realize, oh, there are 200 cases. My solution would be correct, would be good enough for one case. Actually, I did see the 200 cases, but I also saw that you have 6 seconds available. I thought, oh, well, somebody put it under knapsack, and then I thought, oh, maybe that's good enough. But actually, it isn't good enough at all. So anyway, what is the problem? In this case, I'm not really going to tell you or show you the code because I think this is quite involved. But I want to show you explain the technique, and then if you're more advanced or if you want to try, you can look at my solution, or you can talk to me about how to do that or try it yourself. Okay, so what is the problem? You have up to 200 games, so we don't care about that part too much. So we'd look at what each game does. So each game, you have 3 lines. The first line has M up to 30, which is the number of tiles in the bag. Then you have a bunch of labels. Each one is between 1 and 10,000. The third line, it contains 2 integers, N and T, which is the number of tiles that you pick from the bag. So you pick N out of M, and then T is the target that you're trying to hit up to, well, less than 10,000, so 9,999. And the problem basically asks you how many ways can you do this? How many ways can you pick N tiles out of the M that forms a sum T? Now, this is a little bit different because I have a certain number of items, M, but I have to choose N of them. And N could be any number between 0 and M. So the number of ways you can choose N things out of M, of course, is M choose N, the binomial coefficient. And if you know binomial coefficient, you know you have a Pascal triangle. The biggest entry is always the one in the middle. So how big can this be? If M is at most 30, the biggest it can be is 30 choose 15. Okay, so what is 30 choose 15? Let's ask Google. And it's approximately, so why is it approximately instead of exactly? I don't know. Anyway, I guess that's what AI gives you. It's 155 million. So the main thing is you cannot try them all because there are too many. So you can't just say, let's try all M choose N, and for each one, sum it up and see if it works and then count how many would have worked. That doesn't work at all. So then you can try some kind of, dynamic programming thing like this. F of M and T to mean that's number of ways to choose N out of M items, first M items with total T. And you can use the same kind of idea. So F of M and T, it's equals to either you choose the last one or you don't. So if you don't choose the last one, you still have to form the same sum. You still have to pick N things, but you throw away one of the items. Or you choose the last one. So the value of M minus 1, sorry, not here. You choose the last one, so you have one fewer things to choose, and T minus the value of M minus 1. The number of ways you do it, you choose the last one. The number of ways you don't choose the last one, you add them together. That's the answer. And then plus the appropriate base cases that you have to deal with. And you write this and you say, okay, how bad can this be? This is at most 30. This is at most 30. And this is at most 9999. So altogether is roughly 30 squared times 10,000. 30 squared is 900. And then you have 4 more zeros. 9 million. If I haven't screwed up. And you say 9 million, that's nothing for 6 seconds. And that's really good enough if there were not 500 cases. Okay, so now it turns out that this is not good enough because if you have 500 cases, it's too big. And we want to somehow make this smaller. So what are we going to do? So we're actually going to, believe it or not, we're actually going to brute force this whole thing. And we're going to do it in the most naive way possible. With M objects, so M tiles, we can try all possible subsets of M tiles. Okay, you may say, well, what am I really talking about? Because there's so many of them, but let's ignore that for now. Try all possible for each subset. Find what? Size of subsets. And the sum. And we'll say that the number of ways to form, so let's call this size, let's call it sum. The number of ways to form a certain sum with a certain size of subset plus plus. So I have an array that says that I have another way to form a certain sum. So sum is, I don't know, 35, and then you use 2 things. So then I have found one way of using 2 elements to add up to 35. And I'll do that. I'll do all of it. Of course, I can say, well, you don't care about size more than M, but so the sum is up to 9999, and this is up to M. But you say, well, what am I actually dreaming about? Because trying all possible subsets, there are 2 to the M of them. I don't even care what size they are. I mean, I know that I'm trying to hit a certain, I'm trying to choose N tiles out of M. I don't really care. Just give me everything. Even if I'm trying to choose size of subsets that are bigger than N or smaller than N or whatever. I just get them all. All right, it's really easy to cover. But of course, 2 to the M, it's impossible when M is 30. But this is where we're going to make the breakthrough, I guess. When you have a problem that it's about 2 to the 30-ish, and as you just say, basically 2 to something, where 2 to something is too big. But if you can divide, you can make it into half, and this is okay. Right? So if M is 30, then this is 2M over 2 is 15. And 2 to the 15 is only about 32,000, roughly. And that's okay. But why do I want to do half of it? And this is where we're going to look. Okay. So I have M items. And I want to pick n things out of it so that the total sum is a certain value. I can't remember what the letter is, but I'm aiming for some total sum s, whatever. What am I going to do is I'm just cut this in half, m over 2, m over 2. Okay, if it's m is odd, then you have to round up and round down in one. But let's just pretend that you split up evenly. Now, if I want to find a subset that add up to S, either that subset it's completely inside here. Okay, so if I have ways left and ways right, so I look at the first half and I do this whole thing and I get all of the different number of ways to form a certain sum here. I can do this here over here. I can do this over here. So I can figure out all the sum, how many ways I can form a sum S when the subset is entirely inside here or entirely inside here. So those I can do because I already computed it. But there will be subsets which require some things from here and some things from here. So how do I know how many of these types there are? Well, first of all, how big is the thing from the left? I don't know. But we can try for left size from 1 to n minus 1. Okay, why 1 to n minus 1 and not 0 to n? Because I am forcing you to only consider subsets that requires both sides. So if it requires 0 on the left, then it only requires the right. So I only want to know the ones that requires both sides. Okay. But also if I'm trying to make S, how does it split up? You can have a certain, maybe this part add up to something and then this part makes up the rest. So if S is like 100, maybe this one makes 1 and 99 or 2 and 80, 98 and so on. I don't know. So I'm to try all the other ones. Basically, I have to try all of them from left sum, again, from 1 to S minus 1. And then I say the number of ways left to form the left size, left sum, and left size. The number of ways I can form, I don't know, using the sum, I don't know, 10 and n equals to 3. Well, if I'm looking for total size n equal to 10, then over here I'll be looking for n equals 7 and s equals to 90 because I'm trying to make the sum 100. So, and if there are 5 ways to do it this way here, 10 ways to do it here, then each pair is possible, so it's 5 times 10. So I have to multiply the number of ways on the right of the total sum minus the left sum, and then the total size minus left size, and then add that into my accumulator of the answer. Okay, so basically I split it in two. I look at the solutions completely within the first half. I look at the solutions completely within the second half, and then I try to look for solutions that split across. And combining these two are basically I guess you can call it the knapsack problem. Because I have a bunch of items of a certain size, a certain capacity, in this case a sum, and then sort of value. And so I guess actually the capacity is both. The capacity in this case is actually a two-dimensional thing. It's the sum and the size. And you try to add up to exactly that capacity. Okay, so this is sometimes called a meets in the middle approach. You split it into two and then you kind of pick the two sides and try to match them up. And it's a way to reduce a problem of complexity 2 to the m, which might be too much, to 2 to the m over 2. Okay, so this is definitely way more advanced than the other two, but since I I guess I accidentally chose it and I did it anyway. Might as well explain it to you in case you find this stuff valid. Okay, so I'm gonna stop here for this week, and hopefully you'll get a chance to do some of these problems, and I'll continue again next week.